In the previous two videos, we developed a conceptual foundation for understanding power series representations and approximations. In this video, we apply this knowledge to obtain a power series representation for the sine function. We let f of theta equal sine of theta, and we choose theta e equals 0 as our expansion point. We draw the plot of sine of theta versus theta, including a little neighborhood around theta e equals 0. Before we construct the power series formally, we develop some intuition about its qualitative appearance. In the vicinity of theta e equals 0, the plot of sine looks like the slanted fuchsia line. Of course, if we move beyond this immediate region, deviations become noticeable. The fuchsia line overshoots the turquoise curve as theta increases. This suggests that sine of theta can be approximated, at least near theta e equals 0, in terms of some sort of linear term that's positive constant stuff times theta minus more complicated corrections that bring us down from the overshooting fuchsia line toward the correct turquoise curve. Now that we have taken a guess as to the qualitative properties of the power series expansion we seek to construct, we deduce its terms more carefully. We need to write out the quantities that appear in the sum. To do this, we will fill out the entries of this table. For the term with k equals 0, we are interested in the zeroth derivative of f, which is another way to say f of theta. This is sine of theta. When k equals 1, we want the first derivative of f. In the slide deck on derivatives, we found that the derivative of sine was cosine. We also said that the derivative of cosine was negative sine, so the sines and cosines keep coming back to themselves as we calculate successive derivatives. You may wish to return to this slide to confirm the entries for d squared f d theta squared, the second derivative of f, and so forth. Now that we have filled out the first three columns, including the column of expressions, we work on the next column by evaluating the expressions at the expansion point theta e equals 0. The height of a right triangle subtending 0 arc length on a unit circle is 0. Thus, sine evaluated at the expansion point theta e equals 0 is 0. The horizontal width of the same triangle is 1. Cosine evaluated at theta e equals 0 is 1. Likewise, subsequent values of higher derivatives evaluated at theta e equals 0 will be 0, -1, or +1. To fill out the next column, we simply write out values of k factorial. Finally, the information we have gathered on this table can now be assembled in the last column. For example, look in the row with k equals 1 at the last entry. The contribution to the sum is 1 over 1 factorial times theta. This is 1 over k factorial, where k factorial is 1 factorial, times df d theta, where df d theta is 1, times the first power of theta minus theta e. Please pause the video to check that the contents of the row describing k equals 3 are consistent with the final entry, minus 1 over 3 factorial times theta cubed. The terms in the column to the right are added up together as the first pieces of a power series representation for sine of theta. We have just expressed sine of theta as theta minus theta cubed over 3 factorial plus theta to the 5th power over 5 factorial minus theta to the 7th power over 7 factorial, and so forth, with terms with alternating positive and negative coefficients attached to odd powers of theta. This result is consistent with the intuition we developed earlier. This series expansion contains the linear term and initially negative corrections we originally obtained by qualitatively inspecting the plot of sine of theta versus theta. The plot of cosine of theta versus theta is the same shape, except shifted horizontally so that it starts at theta e equals 0 with the value 1 and then descends. The viewer can verify that the power series representation for cosine, expanded about theta e equals 0, contains this initial value, positive 1, with a negative quadratic term that pulls the cosine downward with increasing theta, plus higher order terms. These terms explore even powers of theta with alternating positive and negative coefficients. Now that we have obtained a power series representation for sine, we should ask what we can do with it. In the next video, we work through an example in which we approximate pi to 4 decimal places.